So we want to derive the solution for this wave equation problem, where we have a square uxx equals utt, that's the PDE, and we have the boundary conditions, initial displacement, that's the initial condition, and initial velocity, that's another initial condition. Okay, so we want to use the method of separation of variables. For we start uxt, that's the displacement at any length x at any time t, b x as a function of x, and t as a function of time. Okay, let's say that's number 5, be the solution, and this should be non-trivial solution. Okay, this cannot be identically 0. Now we plug this 5 into 1, equation 1, to get a square uxx. When we find the partial derivative of this with respect to x, again with respect to x, so x is single variable of a function of x, so it will be just x double prime, just the regular derivative. I'm dropping this x and t, so t, that's the left hand side, is equal to utt, x constant, t double prime. Now let's divide both sides by a squared t and x. We get x double prime over x equals 1 over a squared t double prime over t. Now we have this fraction, which is a function of x on the top and bottom, function of t top and bottom. They are equal. That means each fraction should be a constant. Let's say negative lambda. Now we set the first fraction equals negative lambda and second fraction equals negative lambda as well. That implies first fraction equals negative lambda, we get x double prime plus lambda x equals 0, 6. Second fraction equals negative lambda implies t double prime plus lambda a square t equals 0. Okay, now let's plug this u again in these boundary conditions, so that we'll have some new boundary conditions, and with those boundary conditions we want to solve 6 or 7. Okay, so again plug 5 into 2, the first boundary condition, u 0 t equals 0. We get, okay, so 5 is here, so when we plug in u 0 t, so x variable is 0, so this will be x 0 t, that's the u 0 t equals 0. So we have a product of two things equals 0 using the basic 0 factor property, that implies either x 0 equals 0 or t of t equals 0 for all t. But t of t equals 0 makes 5 0. That means we get a trivial solution, so that cannot happen. So x 0 equals 0. Now if we use the second boundary condition, so similarly x at the other end l equals 0 as well. Now we want to solve 6, this ordinary differential equation with these boundary conditions. Okay, we solve 6, that's x double prime plus lambda x equals 0, and x at 0 equals 0, comma x at l equals 0. And if you recall this eigenvalue problem, we've solved this earlier, and the solution will be for this, okay, this should be 7 already, so let's make this 8. Solution is then x as a function of x, but there will be infinitely many solutions, so we put x and x equals sine n pi over Lx for all n bigger than equal to 1, 2, 3, 4, and this solution is valid for only particular lambdas. So eigen values lambda n's are n square pi square over L square. For other lambdas there is no solution. Okay, that for all n bigger than equal to 1. Okay, so we found the x part. If you go back and see number 5, that's the solution. Solution u is in fact a product of x and t, and we just found x. Okay, we just found x over here. Now we need to find, these are the x. Now we need to find the t, and for we use equation 7. Now we want to solve 7, this ordinary differential equation, and if we go back and check, there are two initial conditions to be used. So I want to use third initial condition because this is simpler. We have 0. Now plug 5 again into equation 3, the first boundary, the first initial condition. So plug 5 into the initial condition u x 0 equals 0. We get u is a product of x and t, so x is a function of lowercase x times t 0 equals 0. So we got a product of two things 0. So either x for all x 0 or t 0 is 0. But x 0 for all x makes the solution u trivial. So that's not going to happen. So this gives us t at 0 equals 0. Okay. Now we want to solve equation 7. This 7 for this initial condition t0 equals 0. Okay, now we solve equation 7, which is t double prime plus lambda a square t double prime plus lambda a square t equals 0. That's 7 for this initial condition t at 0 equals 0. Okay, so let's solve it. Let's say this is 9. Now this is second order ordinary differential equation. To solve 7, we find the characteristic equation. So characteristic equation is r square plus lambda a square equals 0. That implies move lambda a square to the other side, so r equals, and take square root, we get plus minus root lambda a I. That means the solution for 7t as a function of t is, let's put some constant k1 cosine of this root lambda a t plus k2 sine root lambda a t. Okay, that is, by the way, the solution x, what we found over here, those are valid for these lambda n's. Though equation 7 is true for all lambda, we are not worried about other lambdas, because for those we don't have any real solution. We get trivial solution, so we are not gonna work with other lambda n's. So we're gonna put these lambdas, and we have square root of lambda, so that's in fact t as a function of t is k1 cosine root lambda is just n pi over L. So this is n pi a over Lt plus k2 sine same thing n pi a over Lt. Now we want to use 9, so using t at 0 equals 0, we get this is 0. Now we are replacing t by 0, so cosine 0, that's 1, so we get k1 plus sine 0 is 0, so whole thing is 0, this implies k1 0. So the solution here, there is no cosine term, this is gone because k1 is 0. Okay, thus we have the solution t equals, this is 0, so k2 times sine n pi a over lt. So pretty much t is proportional to sine function, and to simplify this we can always take k2 be just 1. Okay, but not only 1, we got infinitely many because n bigger than equal to 1, so we have to write tn, or we can simply write without k2, we can take 1. These are sine n pi a over lt, n bigger than equal to 1. So we got tn here, and if we go up we can see xn's, all the x's, these are x, and the product of x and n is the u, because we assumed in the equation 5 u be a product of x and t. Okay, thus we can write down the solutions. Thus u is just the product of x and t, that's equation 5. This becomes, our solution becomes u x t equals, now x was found earlier, that was, look at here, just sine n pi over lx, so sine n pi over lx, and we just found t here, those are again sine n pi a over lt, and we got infinitely many, so we need to put n here as well, un. So these solutions form a fundamental set of solutions, and when we write down their linear combination, that becomes the general solution. So the general solution is then u ext equals linear combination of these solutions. So sum k, let's say n from 1 through infinity, and cn un xt, which are sine n pi over lx, sine n pi a over lt. Okay, and remember we have yet to use the last initial condition, that was number 4, which was utx0, that's the initial velocity, that was gx. Okay, that was equation 4. If you go to the original problem, we get this. Now to make use of this initial condition, we need to find the derivative of this function with respect to t. Okay, this is the general solution. Okay, and let's say this will be the final answer anyways, so equation star, and we need to find cn's, for we use the last initial condition, the second initial condition, and which is given in terms of velocity, so the derivative with respect to time t. So let's find the derivative. Now when we find the derivative of this with respect to t, okay, this is a finite number, since we are saying this is a solution, so we can take the derivative with respect to t, and this function of x and constant, they both behave like constant, we just find the derivative of sine. So this will be n from 1 through infinity, cn sine n pi over lx. Now derivative of sine is cosine n pi a over lt, times, from chain rule we get this factor out. Okay, times n pi a over l. Now we want to use the second initial condition that I just erased, using utx0 equals gx. That was number 4, by the way. Equation 4, we get this is when t equals 0, this becomes gx equals, we can take this constant all the way outside, or let me put it inside, doesn't matter, cn n pi a over L. Okay, sine, we are so we are replacing, look, t equals 0, so we are putting t equals 0, so cosine 0, this will be 1, so just sine n pi over Lx survives. Okay, so gx equals sum cn n pi a over L sine n pi over Lx. But if we think these all being Bns, okay, if we think all are Bns, and this is pretty much the Fourier sine series for this function g, which has a period of 2L. Okay, so I think this is the Fourier sine series of a periodic function g with a period of 2L, and we know how to find these constants. This implies this constant Bn's, in our case Cn n pi a over L, are given by 2 over L definite integral from 0 to L the function gx sine n pi over Lx dx. From this we can find the values of Cn's. Okay, when we move this to the other side, we can cancel L from both sides, so this implies Cn's are I want to bring this to the right side, so 2 over n pi a 0 to L gx, that's the initial velocity, it was given in the question, times sine n pi over Lx dx, and for all n bigger than or equal to 1. So the solution, or in this case the displacement at any time t at any length x, is given by star, and the unknown Cn's are found using this formula, let's say double star. Okay, so hence the solution u is given by star, where the constants Cn's are found using double star, are found using double star. Okay, final. But for the particular question, when gx is given by explicit function, we need to work further. Okay, but in this case gx is unspecified, so we are leaving here. Final.